Now we'll take a look at a component of the multiplication rule that we saw earlier with dependent events. And it was this part called conditional probability. And we read it as a given that probability. So we saw this notation earlier with a vertical bar. It's called a pipe. And I'll review this notation and this formula in the context of a problem. So let's just start with, we have a deck of 8 cards numbered 1 to 8. 1, 4, 6, 8 are gray, 2, 3, 5, 7 are white, and we'll pick a card at random. And it says, find the probability the card is even. So in this case, we'll be considering all the cards in the sample space. So we're not placing a condition yet on the cards. It just says probability of getting an even. So the sample space, okay, so our sample space, all possible outcomes, and I'm going to abbreviate that with a capital S as we did when we started probability. So I'm going to write the formula here for classical probability. If we want to know the probability of even, we would take the number of cards that are even and divide by the number of items in our sample space. So my denominator here, we are looking at all 8 cards, and then the number of those that are even would be, so 2, 4, 6, 8. So there's 4 even cards out of the 8. So there would be a 0.5 or 50% chance of randomly picking a card among the 8 that's even. All right, and I'm just, again, writing fraction decimal percent just for practice. Okay, so let's get to what we call conditional probability. So it starts the same, find the probability the card is even, but now it says given that the card is gray. So what comes after the given is called our condition, and it tells us which cards we're allowed to consider. So rather than the entire sample space, we have to restrict ourselves to only looking at the cards that are gray. So that's why I wrote over here, let's just list the gray cards. So 1, 4, 6, 8 are gray. 1, 4, 6, 8 are gray. So we have 4 gray cards. All right, so this statement is the probability of even, and then that vertical bar, it's called a pipe, but you just read it given. So the probability of even given that the card is gray. So I'm going to write this problem using the formula, and the order here does matter. The first is the probability component. The second is the condition. And I could use this formula that discusses the probabilities, but instead it'll be easier to do it in this format where we keep track of number, little n number. So let me write it with these particular events. So it will be the number of cards that are even and gray. So the numerator is the intersection of those 2 cards that are both meeting criteria being even and gray. And then what we divide by are the number of cards that satisfy the condition. And the condition is the card has to be gray. So whatever is after the vertical bar restricts, tells you the cards that you're going to restrict yourself to. In this case, I'm only allowed to look at the gray cards. So if I only look at the gray cards, there's 4 gray cards. And then among those 4 gray cards, the ones that also are even, so even, I'm just going to circle. So among the gray cards, 4, 6, and 8 are even. So 3 cards meet the condition of being gray, even cards out of 4 gray cards. And that's it. So if you can just remember your condition restricts the cards you're looking at, it hopefully will be pretty straightforward. I'm just going to do decimal and percent just for consistency because I did it last time. But I'm just going to emphasize here with the fraction form. So the probability of even, knowing you can only look at gray cards, the denominator there, 3 out of the 4. originally probability of even with no condition meant that you could look at all the cards, and that's why it was 4 out of 8. So a condition changes your denominator because you'll restrict the outcomes that you're allowed to consider. Okay, let's try another one. So I've got a spinner. Some regions are gray, some are white. And it starts with the probability of getting an even on a spin. So just sticking with my even, I'll go with E. So if there's no restriction, no condition, so no restriction of the slices you can look at, you're allowed to look at your whole sample space. So my sample space, 1, 2, 3, 4, 5, 6. So if you're looking at your whole sample space, I've got 6 slices. And then of those 6 slices, the number of those that are even, right? 2, 4, 6. So I've got 3 even. All right, so similar to the last one there, it would be a 50% chance of spinning and getting an even. But I'm just going to focus on how things are going to change here in the fraction form. All right, so what if we were asked probability of spinning an even given that we know the region is gray? So we're only allowed to consider gray. So the gray regions were 1, 3, 5, 6. So I'm going to write the formula another time. If you can do these without the formula, totally fine. But the formula would be, we would count the number that meet both conditions, this case even and gray, and then our denominator tells us we have to restrict ourselves to the number of cards that meet the condition. So the denominator is your condition. And that's why I'm writing the condition values. So you only consider those cards. Or slices, I guess, sorry, slices. All right, so there's 4 cards that meet the condition. And of those 4, the number that are even and meet this condition of being gray. So among that list of 4 cards, there's just 1 even. So 1 in 4, and I'll just leave it as a fraction. So there's a 1 in 4 chance the spin is even if it's known to be among the gray regions. All right, so let's switch the order here. What if it had been the probability of gray given it's even? So if the condition is even, you're only allowed to look at evens. The evens were 2, 4, 6. So we're looking at the number that are gray and even, meet both conditions among the ones that are even. So condition is your denominator. So I'm only allowed to look at those 3 even slices. And among those 3 even slices, the ones that are gray, white 6, is the only one that is gray. Oops, sorry. All right, well, that was awkward, but I'm back. Okay, gray and even, yep, 1. So 1 out of the 3 evens is also gray. All right, let's try another one. And we'll do this one with a table. We saw these values actually in another problem. So I'm going to do a little bit of totaling. This was about people that went to a fitness studio. I think there were 100 people that went this particular day 40 of them took a yoga class, 20 went to boxing, dance, 10 went to boxing, 30 went to Pilates. And if we add those up, that'll be 100 people. But then they also kept track of whether they were a new customer or returning. And the new was 36, and then the returning was 64. So it's called a two-way frequency table. We're keeping track of two things, new or returning, and we're keeping track of what class they went to. Okay, if we pick a customer at random, what is the probability that the customer was new? I'll just do N for new. All right, so you can go directly to the answer. I'm just going to write the formula again for people that would like to see it. So this is just classical probability. We keep track of the number that are new over the number of people in our sample space. So if there's no condition, you're looking at everybody in your sample space, which would be the 100 people. So out of the 100 people, the number of those that were new is 36. So 36 in 100 chance, you would get somebody that was new. And again, I'm just leaving it in fraction form because I actually want to compare those denominators as we get to conditions. So the next one is, what is the probability the customer is new? Given that, that's the vertical bar called a pipe, new, given that they were a customer that took dance. So my table, I'll just do a D for dance here. Okay, I'll write the rule. The rule says count the number of people that meet both conditions, new and they took dance. The denominator is the number of people that meet the condition. So the given that tells you your denominator. So I'm only allowed to look at people that went to a dance class. So I'm going to emphasize that even further by just drawing that part of the table. So the condition says you're only allowed to look at people that went to dance. You're only allowed to look at that column. You have to ignore the rest of the table. So for dance, I had 8 people that were new. I had 12 people, I'll just do R, that were returning customers. That was a total of, my total here is 20 people. So the rest of the table doesn't matter. Your condition is you can only look at the 20 people that went to a dance class. And of those 20 people, how many of them also met the condition of being new? So 8 people out of 20 will be the probability of picking somebody that was new. Given that, you're only looking at people that went to a dance class. All right, let's try a different order. What if it had been the probability they took a dance class given that they're new? Right, so the formula, the numerator would be the same, dance and new. So new and dance, or dance and new, same thing. I'm just writing it based on the rule. We usually say this one and that one. So dance and new. And then the key here is the denominator. You're only allowed to look at the new customers. So condition tells you your denominator. And then I'm just going to do this for emphasis again on the side. That means that I can only look at the people who were new. So if I'm only looking at people that were new, my condition, then I'm looking at 12 people, that was yoga. 8 of them went to dance, 2 went to boxing, 14 went to Pilates, and that total was 36. So for my denominator, I'm only allowed to look at those 36 people that were new. And then of those 36 people, the one that also meet the condition of going to a dance class, it was 8 people out of 36. Okay, so I'm rewriting the condition just to really emphasize that if the condition is new, don't get distracted by anybody in the other row because you're only allowed to look at that row. So you don't have to rewrite the row, but again, I'm just kind of doing it for emphasis so you can see this whole process. All right, and we'll go on and do just a couple more examples.